So containers, the original technology came from the Linux world, but Docker is the one which made the containers very popular. And the question comes that why Docker, with so much initial success, did not do as well as people thought it would, and why Kubernetes became so famous. So let's start with the fundamental concept of containers, right? So the containers are a great concept, but they have a lot of challenges with the networking, right? So one of the challenges was that Docker depended upon host IP, and hosts are becoming invisible in the cloud. So let's take a step back here, right? So so you have so the first problem which Docker was solving was that, for example, let's say you have a machine and in which you have two Java applications, right? One Java application runs on, let's say, Java 1.6, another application runs on Java 1.8. Now, can you deploy both the applications on same machine? Now, there is no straight answer here. Obviously, somebody would use VMs or maybe some other kind of trickery, but there is no straight way of doing that, right? And that's just one dependency, right? What if you have this whole stack of dependencies, which you want to do it at a application level rather than doing it at the server level, which obviously the VMs do? So the fundamental value proposition of Docker was that once your application is packaged in the form of a container, like physical containers, right? The application can be run anywhere. You can deploy it anywhere, right? And then obviously rest of the runtime and everything else will be taken care of by Docker. So it was a great technology, and uh, that's the reason Docker got a lot of traction initially. But networking is where, in my opinion, a big challenge came in terms of Docker. Because let's look at the pattern, that what are we trying to abstract here, right? So at one point of time, there used to be these large servers, right? There used to be this huge whole server farm, or rather than they used to be just mostly Solaris machines, right? And they were great. I came here in the dot-com boom where the good-looking, very, very expensive Solaris racks used to be there in every startup. So now the challenge was that are, was there a way to most efficiently use all the server capacity? And there was a challenge there because if you are either you have to use different capacity of servers, so different types of servers, different configurations, and that had its own challenges because then obviously that leads to the whole procurement issue. Or you would always have inefficient use of the hardware resources. When we're talking about hardware resources, as you guys know, we're talking about the four legs of the system, which is the storage, memory, CPU, and the network, right? So these are the four things we're talking about here. So that's where the role of virtualization came, and that's the reason VMware became one of the most successful companies. That because VMware's idea was that you buy few configurations of a few profiles of the hardware, and then you are going to run VMs on that, and then VM can run whatever OS you want to run, and that's going to take care of all of your operating system needs, right? And that's the reason that it was so successful. Now, as you know that when you are using VM was a host, if you think about it, right? That an application running inside a VM would not know whether the application is running inside a VM or inside a physical host, right? Now, when we are going to the next level of abstraction, we should get the same experience. And Docker provided part of that experience. Why? Because, as is shown in the slide, that though Docker containers were abstracted at a higher level, but they were still using the host IP. And that had tons of challenges. Number one is that breaks the promise that a container is a host. Like as I said, that you could say VM is a host, right, for all practical purposes. But container was not a host because of these regions, right? And because it was binding to the same host IP, then there were dependencies on port bindings, and they always led to more complexity related to port mapping, and as you can guess, port collisions. So, I mean, think about it. Anything. I mean, you take Postgres, right? Let's say you have one container running Postgres, and its port would be 5432. What if you have second container, right? Then what's going to happen, right? So, or 10th container, right? I mean, and so on and so forth. How many you'll fix it, right? So that was the fundamental problem with the containers, right? And that's the reason Kubernetes became so famous because, yes, somebody can argue that Google is a big company and Google pushes weights behind it, but there was also this huge merit aspect to Kubernetes, right? And that is the structure of pod. Because pod, you can say that pod is a host for an application running inside a pod, a service running inside a pod. There is no way it can tell that it is running inside a pod or inside a host, right? Why? Because pod provides all the level of abstraction. You can have storage attached to the pod. A pod has its own IP address. You can have even memory attached to the pod, right? And compute cycles are obviously divided, but even memory. In fact, you can have even in memory database and other things, right? So that way, for all practical purposes, a pod is like a host, and that's what led to the success here. So if you see the uh, containerized deployment versus the Kubernetes deployment, right? Hardware and operating system layers are same container runtime. But if you see, rather than containers, here we are running pods, right? And then a pod can have one or more applications. So that's another thing. A container by definition can only run one application, but in a pod, you can have one key application, right? One application which is actually running your business logic, and then you can have other applications. For example, you can have a sidecar running there. You can have an application which is taking care of, let's say, database connection. Anything and everything uh, is possible there. Obviously, it's unlikely that you would have more than one primary applications running in a pod because that doesn't make sense, right? But you can have as many auxiliary containers as possible. So let's go to the official definition of Kubernetes here. So Kubernetes is an open source system for automating deployment, scaling, and management of containerized applications. It started with the Borg by Google, and it enforces desired state management. So we'll get to state management momentarily. But the interesting part was that when Docker became so famous, at that time, Google said that, you know what, I mean, we are working on even a better technology from last so many years, and then obviously Google not only open source. So what happens at the time of Hadoop was that Google wrote a paper, bunch of papers, and based on that, the whole open source community created Hadoop and associated open source frameworks, right? So this time Google went a bit further. So what Google did was that Google took Borg as a base and then created uh, the open source version of it. So it improvised on it or it decorated it, and that's what became Kubernetes. And not only that, then obviously Google donated money to create a CNCF, Cloud Native Foundation, right? And then the rest is history, right? So and let's talk about the disaster state management. So in fact, when it comes to So there are two fundamental ways of getting to whichever desired state you want to get, right? So one is you care about the means, and another is you do not care about means side. So in case of Kubernetes, the only thing you care about is the end state, and so there's the end state, which is, let's say pod needs to be replicated three times, right? Now you don't care how pods are replicated three times, right? That's the only state you care about, not how part of it, but what part of it, right? So so that is the desired state management, and then there is an open source version of Kubernetes, and then there are a bunch of managed Kubernetes engines. So let's look at some of the Kubernetes distributions in the market. There's a public cloud. There are obviously the obvious three, at least in North America. That is EKS, AKS, and GKE. Then we have Red Hat OpenShift and VMware Tanzu as part of managed services. And then when you're talking about desktop, so Docker Desktop is there, and then obviously we are there. The Zettabytes, the Roost Kubernetes desktop. Okay, so this much for today, and tomorrow we'll start with the basic Kubernetes objects.